Good afternoon, everyone. Or morning. I don't know why I keep every time. I feel like the last few times I've come into this, I've said good afternoon. It's clearly morning. So good morning.
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 Good morning.
All right.
Morning.
Good morning.
Let's see. Hey, we got one in chat. Got a good morning in chat. Thank you, Kiana. There's poll everywhere. I'll post it up again. I want to go ahead and get it up though. If you haven't already. Phone needs to be muted. Chevy joined the wrong meeting. All right, so I've got 11 o'clock. There's the link one more time. I'm going to activate the quiz. Today's quiz is brought to you by the chain rule, because I'm asking you to differentiate the function f of x, which is sine of 5x. Differentiate the function f of x is equal to sine of 5x. You don't need to write f prime of x equals. Don't have to write that. Just tell me what the derivative is. Just type in what the derivative is. Oh, there's the Poll Everywhere link again. Cool. We got most people responded. We've seen some people come in late, so there is the link again. I'll give you all just about another, let's see, maybe to 11:04, which is a minute 10 seconds. So 11:04 is when I'm going to lock. Chevy got in here. Cool. All right, just missing what? 3 responses. So you have until 11:04, like I said, which is in 35 seconds. See if we can get everyone answered today. All right, locking answers here in 5, 3, 2, 1. Locking answers now. All right, so looking at the answers come through, it looks like most everyone got it. One person accidentally misread this as multiplication, use product rule, but they at least use product rule correctly. So that is a bonus. And a couple small mistakes, but the key here is, again, we have to see this as a composition of functions. I have an inner function, which is that 5x. My outer function is sine. So chain rule says take the derivative of the outer function and plug back in the inner function. Derivative of sine is cosine. And then I plug back in my inner function, but that's not all I do, because I have to make sure I also multiply by the derivative of the inside function. And I'm just going to write it out. It means I need to multiply by the derivative of 5x. Well, the derivative of 5x is just 5. Whoops, not equal. And we can rewrite this. Just throw that constant multiplication out front. 5 times cosine of 5x. And 5 times cosine of 5x. As long as you had cosine of 5x and multiplied it by a 5 in some order, you got the answer correct. And it looks like most people did. So kudos, everyone. It was a good daily quiz. Awesome. All right. Same thing. Thumbs up if you're feeling good. If not, please ask a question. And never, ever, ever be afraid to be the one person who just asks a question. Please, please, please. All right, so today we are covering implicit differentiation. Implicit differentiation. And really this is talking about differentiation when we have, or considering how one variable changes with respect to a separate variable, right? And all of our stuff so far, we're always differentiating with respect to x, functions of x. So something like x squared plus 2x plus 1. X squared plus 2x plus 1 is a function of x, and I'm differentiating with respect to x. Right? It doesn't matter what variable I differentiate with. As we've seen in the homeworks, it follows the same thing, right? As long as you're differentiating with respect to that variable, you follow the same rules. So if I looked at the top one, the derivative with respect to x of x squared plus 2x plus 1, I would apply my power rules and constant rule and all that stuff to get 2x plus 2. And then down here, where I'm taking the derivative with respect to y of y squared plus 2 plus 1, because I'm taking the derivative with respect to the variables that I see here, I just follow the same rules. So I take the derivative of y squared, which will be bring the exponent down, subtract 1 from it. Give me a 2y. Derivative of 2 times y, so that middle term right there will just be a 2. And the derivative of 1 is a 1. The question that we're going to answer today, and we talk about today, and you should have watched the videos on, is what happens if I take the derivative with respect to x of, let's say, that y squared plus 2y plus 1. Right? So this is assuming that y changes in some form with respect to x, y and x are related, and then through that I want to find out how y changes with respect to x, the dy dx. I want to find out how y changes with respect to x. So you go to Poll Everywhere, you have your first one up. And chain rule comes into play here. Chain rule comes into play. Okay, so I want you to differentiate. Let me put it on the screen for the recording. Find the derivative with respect to x, that d over dx, of y squared. Derivative with respect to x of y squared. Okay. You can give y'all about 30-ish more seconds just to select your answer. All right, 10 seconds. So select your answer, at least select your best guess. Locking answers in 5, 3, 2, 1. Locking answers now. All right, so this time majority is not correct. So let's see why. Like I said before, we always have this assumption. Hopefully y'all can't hear that truck going outside my apartment. Can y'all hear me clearly right now if I'm talking, or is that too loud? Give me a thumbs up if you can hear me. All right, truck's passing anyway. Sorry about that. Cool, you can hear me anyway, so I didn't have to worry about it. So we're always assuming that our variables are related. So that means y is related to x in some way, in this case. So y is essentially a function of x, though we're not stating specifically what that relationship is. We just know that there is a relationship there. So when I'm actually looking at the derivative with respect to x of y squared, this is a composition of two functions. This is the composition of two functions. I'm going to try to write it super explicitly because y is acting in some particular way with respect to x. So y does something, and then after that is when I square it. So if I have the composition of two functions, I'm going to have to apply chain rule. Now that outer function is relatively easy, and what most of y'all did, just apply the power rule. So this will be 2 times what was originally inside, the 2 minus 1, just subtracting 1 from it, but then I always have to make sure I multiply by the derivative of what when it comes to chain rule. Take the derivative of the outer function, plug in the inner function, then multiply by what?
Y?
The derivative of the inner function.
Yeah, the derivative of the inner function. So I need to multiply by the derivative of y. That's an unknown, right? That's what we just said. I said right before. We want to find it. And the way we always rewrite it, instead of saying d over dx of y, we say how y changes with respect to x. Both of those statements are the same thing. You can essentially just see us as bringing that y up into the numerator. It's funky with the notation in that it's not actually following your multiplication rules, but we kind of see it happening. And that's purposeful to try to make some sense between the mathematics we're doing and the notation that we use. But that just means if I simplify this down, it's 2y times how y changes with respect to x. So I took into account how y squared changes. That's the 2y, but then I also have to make sure I account for how y changes with respect to x, because my overall goal was to find the derivative with respect to x of y squared, of a different variable. So then, really quickly, d over dx of y cubed. Would you take a moment to just write this out on your own paper, solve it out? It's not going to be on pull everywhere. What is this answer going to be? I'll give you all
Wouldn't it be 3y?
derivative of y cubed with respect to x. With respect to x. Nope, you don't need to type it in chat, but thank you for typing something. So, I'm not going to ask you all to submit your answers like I usually do. I'm just going to ask you to follow along and see if you got the same thing. So, again, when we're taking the derivative with respect to one variable, we have a different variable, we have to apply chain rule here. So we have this underlying assumption that our variables are related, that y does change in a particular way with respect to x. So again, I would see this as d over dx of a function cubed, which means that I have to, again, apply chain rule. Take the derivative of the outer function, which is just a cube function. So I bring my exponent down, rewrite what was inside, which was just a y, and then subtract 1 from the exponent. 3 minus 1 is 2. But then I need to make sure I multiply by the derivative of the inside, that dy over dx. That's how I account for how y changes with respect to x. And then just simplifying some of the stuff that we have here, the final answer that you should have gotten was 3y squared times dy dx.
Okay, I have a question.
Yeah, what's up?
So if this wasn't like a quiz or like a worksheet or something, and we put 3y squared, it would be wrong.
Yep, it would be wrong because you didn't apply chain. Good question, and thank you for asking. All right, so as I said, actually, hold on, sorry. Thumbs up if you're good. Ask questions if you have them. Let me start there before I move on. Thumbs up if you're good. Ask questions if you got them. Well, it's a scattering of thumbs up. So mostly thumbs up, and I'm not hearing anything. All right. So, as I said before, that dy over dx is something that we're going to usually want to solve for. It is an unknown, and that's what we want to find. And usually when we see implicit differentiation showing up is when we have implicit functions. So that means that y is not a specific function of x, and the best example of that is a circle. So if you take the equation of a circle, which if you remember this from a pre-calculus, if you got to cover it in a pre-calculus class, this right here, x minus h squared plus y minus k squared equal to r squared. This always creates a circle with radius of r, and the center of the circle is at that point hk. Just a reminder, not something that you need to memorize. This is just saying what this creates is a circle, and it's a circle. The graph of the circle doesn't describe a function. Well, the answer is no. Right? If I drew a circle anywhere and I tried that vertical line test, it would clearly fail. Right? It would clearly fail because if I tried to plug in one x value, there's 2 potential y values that could be the outputs. This is what is called an implicit function. This is why we do implicit differentiation. However, I can see with that circle, I can still draw tangent lines for various points, which gives me an indication that I can probably find a relationship for how y changes with respect to x, but instead of it only depending upon my x value, it's going to have to depend on both my x and y value. So we can still even differentiate things that are not explicit functions, but are also implicit functions. So if you go back to your poll everywhere, you have a new question up. Okay? You have a new question up. So you're going to want to find how y changes with respect to x, that dy over dx by implicit differentiation. And the equation that you're given is x squared plus y squared plus 9. Actually, let me share it. I wanted to leave that up for a second though. So I want to take this equation, x squared plus y squared plus 9. Take the derivative with respect to x of both sides. Take the derivative with respect to x of that entire equation. And once I've calculated all those derivatives, as we saw, we should get a dy over dx to appear. Once I've done that, I want to solve for that dy over dx. That is my unknown that I care about. And like I said, you should get a function of both x and y. Your answer should have both the x variable and the y variable in it. So take a moment, take the derivative with respect to x of both sides of this equation, solve for dy dx, and tell me what you get. Ooh, we got some responses in already, and they're looking good. Yeah, and just to save you some time, you don't need to type in the dy over dx. If you had, that's fine. Just type in what dy over dx is equal to. Just to save you a little bit of time typing. But most of the answers that are coming in are good. So again, you're trying to solve for dy over dx. I'll give you all till 11:24, which is a minute 15. 15, just so we can make sure that we're moving along. Cool. Got over half of y'all responding. That is good. All right, you've got 30 seconds left if you have not submitted, which is 8 of you. Still waiting for 8 answers. All right, I'm going to lock answers here in 5 seconds. So make sure to hit enter on whatever you got. 3, 2, 1. Locking answers now. All right, so we were missing 4 responses, but I'll say that those of you who did respond, you at least gave me something that is part of the way on the process to finding the answer, though a very, very, very strong majority of y'all did give the correct answer. So let's look at it, right? So I said take the derivative of both sides. This is how we get the dy over dx, how our y is related to x. So take the derivative with respect to x of both sides, which means I take the derivative with respect to x the left-hand side and the derivative with respect to x of the right-hand side. Now, that right-hand side, in this case, is relatively easy to calculate because the derivative of any constant is always what?
0.
0. So on that right-hand side, I'm going to get 0. The left-hand side is where I'm going to have to be putting in a little bit more work. And what I'm just going to do is just take it step by step, apply some simple derivative rules so I can focus in on the important parts. Okay, and make sure we're all following along. So I can split that derivative over a plus sign, which means I just need to consider the derivative with respect to x of x squared and the derivative with respect to x of y squared. Now, the derivative with respect to x of x squared, those variables match up, which just means I've applied the power rule, which means it's going to be 2x. But what did we just say the derivative with respect to x of y squared is? What did we say the derivative with respect to x of y squared is?
We're going to 2y dx over dy or something.
dy over dx. How
Okay,
y changes as x changes. Okay? So it's that 2y dy over dx because, again, we're assuming we know y is related to x in some manner. In fact, we know it because of this equation overall. So I can apply my power rule to the y variable, which is just bring the square down, subtract 1 from it. But then I have to, because of chain rule, make sure I multiply by how y changes with respect to x, that dy over dx. So this leaves me with the equation 2x plus 2y times dy over dx is equal to 0. So if you got to this part, you did the implicit differentiation correctly. So that's a check mark right there. But what was the goal of this problem was to find dy dx, figure out how y changes with respect to x, which means that I need to solve for dy dx, i.e. get it on one side by itself and then have everything else on the other side. So one good thing to do would just be to subtract a 2x from both sides, just leaving that dy over dx where it is, and then divide by what I'm multiplying it by, which is a 2y. I have to come over here to the right-hand side. So then this would be a negative 2x over a 2y, and does that simplify at all? Absolutely, right? Because I'm multiplying by a 2 and dividing by a 2. And I get negative x over y. So for this equation of this circle, x squared plus y squared equals to 9, I can always find the slope of my tangent lines. Now my y changes over my x changes. My derivative with respect to y, it depends upon both your x value and your y value. Okay? So that is the formula. Let's see it in action. So I'm going to give you all a second just to finish writing it out. You're following along, and then we're going to look at a graph real quick. Give me a thumbs up when you're done writing. How about that? And if you've got questions, this is the perfect time to ask. Thumbs up if you're good. Ask a question if you got it. All right. So let's look at that circle. So here on Desmos, I can zoom in just a tad bit. I have the equation of a circle. That is the equation of that circle, x squared plus y squared plus 9. And I told you, you can find the equation of a tangent line, or the slope of your tangent line, just by looking at your x coordinate and your y coordinate. Here, just because I have to set some variables, otherwise it'll be a little funky with me. A corresponds with my X value and B corresponds with your Y value. I'm just saying, okay, I have a range of values that I can set A, and I see from that slope function, I'm getting, as we would see here, if I'm in the negative values for A and positives for Y, so on this point, I'd see I have a positive slope for my tangent line. And as I move to the right, I'm also going to get a negative slope. Anywhere over here would be a negative slope. And this makes sense because I have a positive X and a positive Y. My formula is a negative times X over Y. So we get negative slopes there. If I ignore this real quick and I type in a minus, so we can look at the bottom half of the circle, I can still see that this gives me the slope of the tangent lines at any single point. I can keep rotating around that circle depending on where my X and Y values are, will give me various slopes. So even when I don't have functions, I can still find slopes of tangent lines. This is one of the reasons that derivatives are so important. It's because we know in the real world not everything is a function. We can have some weird looking shapes, especially if you get into physics. Physicists love this stuff. And it's because derivatives, even though we don't have a function, we can still talk about how a function is changing. We can talk about the slopes of the tangent lines for those functions at any point. So, questions, I guess, while I got this graph up before we move on, we're going to do more implicit differentiation practice. I wanted y'all to see the actual demonstration. You use that slope and you can get the slope of the circle at any point. Use that equation to get the slope of the tangent line for the circle at any point, I should say. So yeah, thumbs up if you're good. I already saw a couple pop up. I have everyone's. Otherwise, please ask a question. All right, so I'm going to stop share for a moment so I can get the next problem up. So now we're just going to get more practice with implicit differentiation. Okay. So if you go to poll everywhere, you now have a new question up. Okay, so for this one, again, I want to find dy over dx. So I want to find how y changes with respect to x. For the equation sine of y plus cosine of y is equal to 3x squared plus 4. And again, just like the last equation, the starting step is to take the derivative with respect to x, because I want to find out how things are changing with respect to x, specifically how y changes as x changes. And if I want to figure that out, I got to take the derivative with respect to x. And again, with implicit differentiation, when we're kind of mixing our variables, again, chain rule applies here. Chain rule applies. All right, so I'm gonna give you all like 4-ish minutes to do this. So I'm gonna say 11:37 is when I'm gonna lock answers. Take your time. Give it your best shot. keep giving you all a timer and heads up. You've got just under 2 minutes left. So we can make sure that just we're moving on. All right. Overall, good answers so far. All right, so it's 11:37. So it's about 30 seconds from now. I'm going to lock. And this is just so we can make sure that we're moving along. So please give me your best guess at least. And you're trying to find dy over dx. You're trying to solve for dy over dx. All right, I'm going to lock here in 5 seconds. 4, 3, 2, 1. Locking answers now. All right, so just want to show y'all, we'll have to rewrite this on screen. Most people did get the correct answer. I just want to highlight this. Thank you for at least responding and letting me know that you're a little confused. Again, I don't care if you're getting these right or wrong. I'm trying to gauge where we're at as a class. So thank you for at least doing that. So, and also want to point out that I saw a couple people insert an answer like this. If you're trying to type this into WebWork, you'd be very, very close, but it would count it as incorrect. Okay, because what you have written here is 6x divided by cosine of y. If we're following PEMDAS, after I do this division, then I would be subtracting sine of y. What you probably intended was to have cosine of y minus sine of y in the denominator for 6 divided by x. And if you wanted that, you would need to put grouping symbols around it. You need to put parentheses around it. So something like this answer right here. So this is probably what you were trying to convey. Just to give you the heads up, WebWork would have counted the first one we saw wrong. You would count this one correct. Just to try to help save some headaches later on. Okay, but let's do it. Let's go through it now that we see the final answer. So, equation we were given, sine of y plus cosine of y is equal to 3x squared plus 4. And to find dy over dx, what I need to do is take the derivative with respect to x of both sides. So the derivative with respect to x of sine of y plus cosine of y equals to the derivative with respect to x of 3x squared plus 4. And again, I just look at both sides and say, okay, which one might be easier for me to start with? Or you can start on the left and work to the right. It doesn't really matter, your choice. There are multiple paths in this forest. But if you look at this for a second, that right-hand side is probably the easiest one to solve, right? I can take the derivative with respect to x of 3x squared plus 4. That's a polynomial in terms of x. I don't have anything funky happening there. I just apply my power rule and the constant rule. So this will end up just becoming 6x. Derivative of 3x squared is 6x. The derivative of 4 is 0. Add those together, I'm just left with 6x. Now on that left-hand side, I see I have some y terms. So that's where I'm going to have to be more careful. So let's again just take it step by step, make sure I can isolate the derivatives that I need to calculate. So I can split that derivative on that left-hand side over the addition. So this is the derivative with respect to x of sine of y plus the derivative with respect to x of cosine of y. And again, here I'm going to have to apply the chain rule because inside of both my sine and my cosine function, I have something that is not x. Right? It is y. It is related to x in some way, but it is not just x. So if I take the derivative with respect to x of sine of y, well, I take the derivative of my outer function, which a lot of y'all did at 100% correctly. Derivative of sine is cosine. I plug back in what I had, but then I need to multiply by the derivative of inside. Well, the derivative of what is sine is the derivative of y, so I need to multiply by dy over dx, the derivative of y with respect to x. And a similar thing happens for this second one, the derivative of cosine of y. I'm going to add to it, well, I take the derivative of the outer function, derivative of cosine, which is negative sine. I plug back in what was inside, and then I multiply by the derivative of the inside. Again, the derivative of the inside is the derivative of y, so it's just dy over dx. It's an unknown, something we're going to solve for. This is equal to 6x, and then most of y'all probably jump straight to here. I'm just going to rewrite that second term on the right-hand side. So that last line, I'm just kind of cleaning things up a little bit with that negative. So I have cosine of y times dy dx minus sine of y times dy dx equal to 6x. And I'm trying to solve for dy dx. And what do both of those two terms on the left side of this equation have in common? Someone please unmute themselves and tell us.
Isn't it the cosine minus sine? Why?
So that is what is there. But between both those two terms, they don't both have a cosine term in common or a sine term in common. What do they both have?
dy over dx?
Yeah, they have that dy over dx. And for both of those, cosine of y and sine of y, I'm multiplying by dy over dx, which means I can factor it out, leaving me with cosine of y minus sine of y times dy over dx is equal to 6x. Oops, that. And underline just so you see the derivatives. I meant to do that before. But then the last thing is to solve for dy over dx. So I have something times dy over dx. To get rid of that something, I just divide by it. I'm going to have to just kind of come right here. I don't really have too much room, and I don't want to go to a new board. Well, then my dy over dx, how y changes with respect to x, is going to be 6x divided by cosine of y minus sine of y. And that would be my final answer. Any questions? If you got them, thumbs up if you're feeling good. Please, please, please ask questions if you got them. A nice scattering of thumbs up, but I'm not hearing any questions, and I want to make sure you get time for this last problem. Okay, so go back to poll everywhere. We've got one more problem. Okay, so I want y'all to again find dy over dx by implicit differentiation. And the equation that we're given is sine of y times tangent of x is equal to cosine of y. Sine of y times tangent of x is equal to cosine of y. Okay, I know it won't be enough time to necessarily type in your answers, but I'm going to give you all a minute and a half just on your own paper. Get through as far as you can. Because I know me, I like to talk. So I'm going to need at least 3 minutes to get through this. All right. And just heads up, 50 seconds and 50 seconds. Please come back to Zoom. Or if you're done solving it already, maybe go ahead and do it. Go ahead and come back. All right. So I know that wasn't a lot of time to kind of get through that problem. Hopefully you got at least through some of it, but I want to make sure that we go through it. Ooh, we got 2 responses already. They look about right. So let's see. All right, so I want to take, again, the derivative with respect of x both sides and then solve for dy over dx. So take the derivative with respect to both sides means I'm taking the derivative with respect to x of sine of y times tangent of x. And I need to take the derivative with respect to x of cosine of y. Okay. So I get to decide which side do I start with first. And it really doesn't matter because I'm going to have to do both. Which one do you want to start with? The left-hand side of that equality or the right-hand side of that equality?
Left.
Sure, let's go left. When I look on that left-hand side, I see that I'm multiplying 2 things together, which means I have to use what rule?
Not the product, the product rule?
Product rule. I got to use product rule here. Which means on that left-hand side, the derivative of sine of y times tangent of x is the derivative with respect to x of sine of y times tangent of x. Let's go away with this. So sine of y times tangent of x plus sine of y times the derivative of tangent of x. And then I'm leaving, just for now, I'm leaving that stuff on the right-hand side alone because we just said we're focusing on the left-hand side. So all I did was apply product rule. Then I look at sine of y, derivative of sine of y. Well, I have a y in there, and I'm taking the derivative with respect to x. So I can take the derivative of the outer function. So this would be cosine, plug in my value, but then I need to make sure I multiply by the derivative of the inside, i.e. the derivative of y with respect to x, or dy dx. And I'm still multiplying this by a tangent of x. So just to show, derivative of sine of y was that cosine of y dy over dx, plus sine of y times the derivative of tangent. And what's the derivative of tangent with respect to x? We got no y's in there, so this one's straightforward.
Secant square.
Yeah, secant square. Thank you. Yeah, no, I kept kind of talking, interrupting your chance to answer. But secant squared of x. And now I've already done all my derivatives on the left-hand side. I can do the derivative on the right-hand side. So again, follow the same pattern that we saw in the last problem, derivative of cosine of y. Take the derivative of the outer function, derivative of cosine is negative sine, plug back in what was inside, but then I need to multiply by the derivative of what's inside, dy over dx. So now I've done all of my derivatives. I've done all the derivatives I can. My goal is to solve for dy over dx. So I just need to get all my dy over dx's on one side, everything else on the other. And those algebra techniques that you were forced to learn for so long are finally becoming useful again. So the easiest way that I see it is I have a cosine of y times the tangent of x times the dy over dx, just rewriting that a little bit, that term a little bit. I can add the sine of y times the dy over dx to both sides. And then for sake of brevity, because we need to get out of here, I'm also going to subtract a sine of y times that secant squared of x, because that was a term that did not have a dy over dx. But then again, now I have all my dy over dx terms on the left-hand side. I can factor that out, leaving me with a cosine of y times the tangent of x plus a sine of y times dy over dx is equal to negative sine of y secant squared of x. Let's see if I can fit it up here in that top right corner so I don't have to go to a new board. Then to get dy over dx by itself, I divide by what I'm multiplying it by. So dy over dx is equal to negative sine of y secant squared of x divided by cosine of y times tangent of x plus sine of y. And from there, I can simplify some things down, and I would want to do that because it would make my life a little bit easier when I go try to type this stuff into WebWork. But that is a correct answer. Okay. Take the derivative with respect to x on both sides, make sure I apply the chain rule. And anytime I take the derivative of just the variable y, it becomes that dy over dx. It becomes what I want to solve for, right? How does y change with respect to x? Then once I've taken all my derivatives, solve for dy over dx. Use that algebra that you've been learning. So 11:53. I know I'm over time again. Sorry about that, but at least give me a thumbs up if you have no questions. But if you do have a question, please ask. Cool. All right, I'm not hearing any questions. So I'm going to say y'all are good to go. I'm going to go ahead and stop the recording now.